Data warehouse modeling, the data cubes. So we're going to look at a high level of these data cubes that we use in the data warehouse. So the data cube, this allows our data to be modeled and viewed in multiple different dimensions. So we can choose how we want to look at this data. And while the cube implies three-dimensional, it can really support multiple dimensions. So keep that in mind. So here in this example, product, region, month, this is a three-dimensional version of the cube. And we can have a variety of different dimensions: time, branches, locations, and have the actual data with the numerical values for each one of those. So we could have things like facts. We are the values. These are the numerical values, like items sold or dollars sold, versus dimensions, these attributes that we're looking at. So in this example, we have sales volume as a function of the product, date, and region. And so again, kind of looking at this in a three-dimensional cube. And where, if you were to go across VCR to Q4 and then down to Mexico, finding that cube, like where that data value would actually end up there. And then when you get to the sum, this would be a summary of all of them going across, and this would be across the entire data set. So here's a data cube example where we have location of two Canadian cities, Vancouver and Toronto, New York and Chicago in US, and then the quarters of the year, Q1 through Q4, and then 4 different types of items being sold: home entertainment, computer, phone, security. And so we can look at all these data points, and if we were to grab like the 30 here, this looks like this would be Q3 in Vancouver for a phone item. And of course, all the values, you can go grab whatever particular spot that you are looking for. So with our data cube, we can look at it as a lattice of cuboids. And so when we look at the attributes or dimensions that we have, we can, for example, let's look at the bottom here. So here, time, item, location, supplier. Those are our 4 attributes that we're looking at. And if we're at the bottom, at the 4-dimensional base cuboid, what we're doing is we're specifying values for each of these 4 attributes. So time, yesterday, item, the cell phone, the iPhone, location, Denver, and the supplier, Apple. So we're specifying the very specifics for all 4 attribute dimensions that we have. All right, so then if we go up, let's say we go up 1 layer in this cuboid, in this lattice, and this first one here, we are going to specify time, item, and location, but we're not specifying the supplier. So it may not just be Apple selling these phones, it could be other companies as well, Target, Walmart, or whatnot. So we're going to grab all that information, still specifying time, yesterday, the item, the cell phone, and the location in Denver. And so you can continue going up with the different combinations based on having 4 attributes or 4 dimensions. What are all the different options that you have of combinations? And when you get to the very top, this is a 0-dimensional or cuboid, or also known as the apex, where we're getting all the information because we're not specifying anything for time. So we're grabbing all times, we're grabbing all items, we're grabbing all locations and all suppliers. So this is basically no restrictions on the data that should be returned. And so when we're looking for patterns, they can occur in different dimensions or different granularity. So you want to play with this lattice, kind of organize into different cuboids to do your analysis to see where you can find those particular patterns, an interesting pattern. So here's another look at that lattice. And again, at the very top, this is the apex cuboid. This is where we're not specifying anything. So it's like star, 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 star for all the different attributes for time, item, location, and supplier. 1-dimensional, you're specifying one of them. So in this example, the item is milk specifically. 2-dimensional, you're specifying 2 of your dimensions, etc. So here's our bottom base cuboid where all the dimensions have a specific value that we're trying to query our data warehouse on. So with our cuboid cells, our base is the raw data. And then when we talk about ancestors or descendants, the ancestor is where in the hierarchy of the cuboids. So here, again, we've got month specified as January. We don't care which location, so we want to grab it for all locations. So this is the many, just like in regex. Item, all of them, and then specific price, 2,800. So with our materialization, we are basically designing or creating our data cube. We can do it multiple different ways, a full, partial, or no materialization. And the reason for this, full sounds like this would be ideal, and it is, but it's cost prohibitive. So full is where you pre-compute all individual cuboids. The problem is we're working with massive amounts of data, and so that's not always efficient or optimal or what we can work with. And so we might look at a partial, which is computing a subset. And then the no materializations, we don't pre-compute anything. We only compute when needed. So it takes the time to process a cuboid on the fly for a client who might be interested in it, but it's not pre-computed. So we do it as needed. So here's an example of a cuboid, and this kind of gives you a concrete example of actual data. Starting at the 0D cuboid, the apex, which is up at the top. Here's the sales, so we have all the values for every other attribute. So for all time, all countries, all types of food or non-food, this is what we end up with. And then we go down to 1D cuboid where we're specifying sales on Q1 and Q2, Q3. So we're specifying a specific for the time. And you can go all the way down here, our three-dimensional cuboids, so we can see an example with data. So just to take a look at what it would look like in the query language, we have defining cubes in our data warehouse. So that's just to give you some idea of what it would look like to be able to define the cube and have it compute it. And when we do the cubes, we do need to use the group by. So if you've done SQL, this is very similar to SQL. And with the group by, you do have to have and specify your count. So you'll have your count inside your SQL. We're just doing this at a high level. So if you're not familiar with the SQL yet, that is A-OK. But for those of you who do know SQL, this is kind of interesting to see. The iceberg cube, this is where the cube contains only the cells of the data cube that meet some kind of aggregate condition. So we're only going to calculate the ones that are significant enough. And so the idea of the iceberg, most of icebergs are underwater. We only see the very tip of the iceberg above the water. So it's kind of the same concept here with the data that we're working from. So when we get down to this SQL example, here's our count. So it's going to do an aggregate from a data table. We're specifying the cube and then are having the count greater than some minimum support. This is our iceberg condition. So we have to meet this threshold is what we're trying to do. And essentially, one cell generates a lot of aggregate cells. Essentially, we're doing a 100 choose 1 plus 100 choose 2 plus 100 choose 3, assuming we have 100 attributes here. So it gets really large. So that's a lot to deal with. So we're dealing with these icebergs. And so with the iceberg cube, the advantages is we don't have to save those values that are below that threshold. So below that iceberg condition threshold that we're specifying. And it's really going to help us avoid this explosive growth of tracking too much data. So efficient methods can avoid computing these unnecessary cells to make it a little bit more efficient to do our calculation, our data mining. So with our computation heuristics, we'll look at 3 methodologies. We're going to look at the multi-way array aggregation, BUC, bottom-up computation, and the integrating top-down and bottom-up. So there's also, these are some general computation heuristics. You can also find some additional ones in the research. So with a multi-way array aggregation, what essentially we're doing, it's array-based, so it's making use of arrays and doing a bottom-up approach. And so in this approach, we cannot do the a priori pruning, which we'll see in the BUC that we can. And this is not good for high dimensions. If you're using, we'll talk all through this course how high dimensional data is really difficult. And so this particular methodology is not good when you have high dimensions. So here's an example of our cube and our original 3D cube. And we can compute these two-dimensional aggregates for each of these 3 dimensions. So we can grab, this looks like over here is the AB. We could grab, this is going up top here, the 2 dimensions here, and then the two dimensions up front here. So we're computing 2D aggregates for all of our dimensions for each of the 3 dimensions here. And the benefit is we can leverage a sequential scan to get the data as opposed to random access, which is a big time saving, essentially. So while we're doing a single sequential scan, we can calculate partials of each of these 2D aggregates while we're approaching that. So it's effectively a more efficient approach. And then BUC is considered it's called bottom-up construction, although it looks like it's a top-down, and that's really just based on whether the authors of the paper had our little diagram flipped, so it looked more like a bottom-up construction than we usually kind of show it like a top-down. So that's a little confusing looking at the wording of BUC versus it really looks top-down. So the BUC constructs the cube from the apex, so remember the 0 cuboid state where you have no restrictions on what you're grabbing from the data, you're grabbing all of it, towards the base cuboid. So that's how you're constructing this cube. So the order processing allows this BUC to prune during construction, and we can use the a priori property. So it consolidates the notions of the drill down. So one thing that's nice about kind of showing this diagram in this way, where it looks more top down, is that you can see this drill down approach that we can use, or roll up when we're looking at it, and then those terms make sense, drill down versus roll up. Roll up where we're going from more detailed low-level cells to a higher level, more aggregated cells. All right, so then when we're modeling in our data warehouses differ again from our operational databases in the design. And so we're optimizing it for efficient querying and not for updating, all right, because our data in our data warehouse usually is not being updated unless you're working on some current research in like streaming data and trying to deal with that. But for the most part, we set up a data warehouse in static. And so we have these dimensions and facts that we're working from, and we can set up different schemas. So we'll look at the star schema, snowflake, and fact constellations. So the star schema, the idea here, we got, kind of looks like a star. Our sales, we got our fact table, and the fact table is really a bunch of pointers to values. So that's what our fact table is. And then our dimension tables, you can see we have time, branch, item, and location. Each of those are our dimensions, or also known as attributes or features. And this is where the values are for that particular dimension, what the details of what it means for it to be a particular item or location or time. And so the sales is the fact table that connects them, essentially. And so the star schema is a simple example where you essentially have a single central point. And then the snowflake is a little bit more expands out than like a star. It's got more of that snowflake kind of look to it. And so when we look at this example, we still have time and branch kind of looks the same. But if we go down to item dimension table, it's also connected to a supplier. So it's getting into more details in that kind of way. And then sales to location to city. So it's similar to the way a relational database would be, but it's, again, remember what the difference is. The data warehouse, we're setting it up to optimize for what we're trying to do, which is to be able to query quicker and different views and dimensions of the data, as opposed to the transaction processing that most relational databases are set up for. And then a fact constellation is just more complex. So we care about lots of information. We may have 2 fact tables in there. We care about sales and the shipping information. And again, this is all set up to be optimized for our OLAP transactions for our data warehouse for data mining processes.